Started recording.
Good morning, sir.
Running. So yeah, in the previous class we did some problems, and in this class as well we're gonna do some problems of Sontag so that everyone.
Sir, you are not audible.
You're not audible. Like I'm not audible at all.
You are audible, sir.
Sir, you are audible, sir.
Yes, sir, you are audible.
Okay. I should be very clear. I mean, the audio should be very clear, ideally. No noise and all. Is it clear audio or is it noisy audio?
Sir, it is fine at my end.
It is clear, sir.
All right, all right. So Sai Venkat is having some troubles. That's okay. Okay, so let's do some problems. Problems. In chapter 3. Okay, so we will do the general table problems. Mm, so we have to find out the following. So for ammonia, we want to find out the phase and the specific volume. Okay, we would like to find out the phase and specific volume, and in Sontag, the properties of ammonia are in appendix B. Okay, so the question is first A, ammonia at minus 10 degrees Celsius and 150 kilopascal. The question is, under these conditions, what is the phase and what is the specific volume? Okay, so I mean, before going into the the table, the actual physical table, let's just see. So we will say V equal to V1 equal to volume ammonia P equal to minus 10, P equal to 150. So when we run it, we get a specific volume of 0.8337. Okay. So I'm gonna write down the computer answers in red. 0.8337 meter cube per kg. And now we also want to know the phase. So how do you figure out the phase from the software? So we simply fetch the quality and then we can copy paste. So if we fetch the quality, when we run the file, we find the quality is 100. So quality of 100 obviously is not possible. We know that quality is bounded between this. Quality is bounded between this, but see, I mean, if we want to fetch the quality for such a case, obviously the computer has to give some kind of indication whether it is between 0 and 1, or is it superheated steam or superheated vapor or subcooled liquid. So when the liquid is superheated vapor, then it will return a quality of 100. When it is a subcooled liquid, it will return a quality of minus 100. Okay, is that clear, whatever I just said?
Yes, sir.
So
Yes, sir.
we get x1 equal to 100, so we will conclude that this is superheated vapor. Okay, so this should be clear. Now we will go to the table. So we are in appendix B of the book. So let's go to ammonia first. So these are the water tables. Once the water tables are finished, we will go to the ammonia tables. This is still water. This is still water, water. Okay, now we have table B 2.1. So I will write here ammonia is table B point 2.1. All right. So first things first, let me draw the schematic. So we will what would be a convenient schematic? I mean we can do it any. So let's do it PV. So the isotherm will be something like this. So on the PV diagram, the pink curve shown over here is going to be the isotherm. So now let us see. So they're telling at minus 10 degrees Celsius and 150 kilopascal. All right. So first, let us assume that this is the 150 kilopascal line. This horizontal line stands for P equal to 150. I mean, the units are implicit. I'm not writing kilopascal over. So now we must first find out what the corresponding isotherm is. So I must first figure out what is the saturation temperature which corresponds to a pressure of 150 kilopascal. Fine, let's do that. Let's go into the table and now we want the pressure entries. So we want to know the saturation temperature at 150 kilopascal. All right. So we will go to the saturated ammonia table and we will go to, okay. So right over here we have an issue. In the ammonia tables, the authors have not given us the pressure entries. So what do? We don't really, I mean, worry too much. What we will, I mean, okay, let's do it. I mean, suppose you were to do it this way. Suppose you want to still do it this way. So let's take a look. This is the table. So let me take a screenshot and put it over here. This is saturated ammonia, specific volume entries. So let me take a new screenshot. And 150 kilopascal is somewhere over here. So it's between this, right? All right. So let me copy this. Let me paste it over here. So this is verbatim from B.2.1 for saturated ammonia. All right. So what do we see? So at minus 25 degrees Celsius, we have a saturation pressure of 151.6 kilopascal. At minus 30 degrees Celsius, we have a saturation pressure of 119.5 kilopascal. So what do you think? What will be the Tsat? The Tsat will lie somewhere over here, right? The saturation temperature corresponding to 150 kilopascal will lie somewhere between minus 30 degrees Celsius and minus 25 degrees Celsius. And it will be obviously closer to minus 25 degrees Celsius because minus 25 degrees Celsius corresponds to a saturation pressure of 151.6 kilopascal. So let's say that this Tsat is minus 25 degrees Celsius. I mean, somewhere in the neighborhood of this. And in our question, we have been asked the state of ammonia at minus 10 degrees Celsius. So if this isotherm is minus 25 degrees Celsius, this isotherm could very well be minus 10 degrees Celsius because as we go towards higher temperatures, the isotherms move upwards. So corresponding to P equal to 150 kilopascal, this is the horizontal line which represents saturation, rather a pressure of 150 kilopascal, and this is the minus 10 degrees Celsius isotherm. So this is the point we would be looking at. So at this point, what is the state? It is obviously superheated vapor. And now the question is, what is the specific volume? We don't know what the specific volume is going to be. All right. So in order to ascertain the specific volume, we must now go beyond the saturated ammonia tables and we must go to the superheated ammonia tables. Fine, let's do that. Let's go to superheated ammonia tables. There we have superheated ammonia tables and the pressure under consideration is 150 kilopascal. All right, so at 150 kilopascal, we directly have the entries, which is very fortunate. And so let me just copy this. Is this visible?
Yes, sir.
So we're required to find out the specific volume at 150 kPa and a temperature of minus 10 degrees Celsius. So when we look at this, so this is B.2.2 superheated ammonia. So under 150 kilopascal, we will first see an entry written in the bracket. So the entry written in the bracket is the saturation temperature, which corresponds to the pressure. That is, in this case, it is 150 kilopascal. So what do we directly get? So corresponding to a pressure of 150 kilopascal, the saturation temperature was minus 25.22, which we almost assumed to be minus 25 degrees Celsius. And if you were to do this interpolation, you would also get minus 25.22 degrees Celsius. Okay. Now, what does it mean? I mean, if we were to look at the curve in PV only, so this is the, I mean, so this is the minus 25.22 degrees Celsius isotherm, and this is the 150 kilopascal horizontal line. This is going to be the minus 10 degrees Celsius. So the entries in the table B.2.2, that is the superheated vapor entries, start off. So if we look at this 50 kilopascal line, maybe 50 kilopascal is somewhere over here. So these tables, graphically, how would you draw the entries in the table? They are starting like this. So for a given pressure, if we were to graphically draw, they are all the entries on this horizontal line. Is this okay? Is this understood by everyone?
Yes, sir.
So you're starting off at just the saturation point, the corresponding temperature at 50 kilopascal. So this is the 50 kilopascal line, and this particular isotherm is minus 46.53 degrees Celsius isotherm. Now this minus 25 degree isotherm will go and intersect over here. So there will be a minus 40 degrees Celsius isotherm which will intersect over here. Minus 30 degrees Celsius isotherm, minus 15 degrees Celsius isotherm, 10 degree isotherm. So all the isotherms are lying on the intersection. So all the points over here are basically lying on the intersection of this horizontal line, this 50 kilopascal line, and intersections of all these isotherms. All these isotherms, as they intersect, you get all the properties. All right, everyone, this should be clear to you.
Yes, sir.
There's one guy is, I mean, possibly few guys will agree, but if in doubt, just rewind this video and you can have a look later on as well. So now, okay, let's get back to the problem at hand. 150 kilopascal minus 10 degrees Celsius. So we have 150 kilopascal minus 10 degrees Celsius. This is the specific volume entry. The specific volume is 0.8336. So from the table, from the actual table, 0.8336 meter cube per kg is the answer that we get. So let's see whether that checks out. 8336, 8337, not bad. In fact, it's pretty good. So let me just save this file. This will be chapter 3 problems. Okay, is this clear? This problem should be clear to everyone.
Yes, sir.
Yes, sir, it's clear.
Sir,
Yes, sir.
could you once explain, like at 50 kilopascal, why the line is like so straight?
Pardon me?
So, like, could you explain at the 50 kilopascal, the
Hmm.
isothermal line is straight in superheated and even in the dome, saturation dome.
So I mean, okay, so this again takes us back a bit, but I'll again explain it, no problem. In the PV diagram, when you're starting off with a liquid, okay, as you keep reducing the pressure, at a certain point, you start sort of boiling the liquid. When you start boiling the liquid at a certain pressure, the temperature remains constant, obviously, and after that, you have this curve. So it's very much similar to the TV diagram that is more easily understandable by everyone. So in the TV diagram, start off. So suppose you are holding the pressure fixed. Let us go back to the thought experiment that you have a piston cylinder arrangement. The mass on top of the piston is constant. So essentially the pressure inside is constant. Okay, when the pressure inside is constant and you heat, so temperature for the liquid will increase up until it reaches the boiling point. Okay, this is just the initiation of boiling. This is just the initiation of boiling. And when actually boiling starts, whatever heat you supply to the system, it's simply going to be absorbed by the system as non-sensible heat. You cannot see a rise in temperature, but it will lead to phase change. So this is what you know as latent heat. That is why the temperature will remain locked over here. And then once everything is converted into vapor, so this is finishing of boiling. Okay, then again the temperature will rise. So this exact same curve, so over here, this is the P equal to constant. This is an iso bar. So when you draw the same diagram, and we have seen that in the 3D model, when you draw the same diagram in a PV diagram, you have instead of the iso bars, you will have the isotherm. So along this P equal to constant. So if you hold the temperature to be constant, meaning somehow you are able to hold the temperature over here constant. In order to maintain the temperature equal to constant, you are reducing the pressure. So when you reduce the pressure, at a certain pressure, boiling will initiate. So this is boiling start. And then as you keep sort of I mean, here you will still add heat. So visualizing this process as a physical process is a bit difficult. But in along this isobar inside the dome, again, this is like where boiling takes place. There is no change in pressure also when this boiling happens. So this is boiling finish. And then again the isotherm, it continues. Okay, so pressure and temperature inside the saturated dome, they will always remain horizontal. They will not have
Yes, sir.
any change.
So, outside the dome is also like straight line in our diagram at temp at pressure 50 kilopascal,
Huh.
or is it
So,
just
No. So your question is, why is the isobar constant? Like, why am I drawing this as 50 kilopascal? What is this?
Not so. So above diagram here.
This one?
For that, yes, sir. For that, this question, like for 50
Yeah.
kilopascal, we have drawn that isotherm, and
Yeah.
outside the dome, we directed a same line. We didn't like make it down.
This pink line you mean?
Yes, a pink line. This pink line.
No, so the pink line is just the 50 kilopascal line. This, so when the y coordinate is pressure, the 50 kilopascal line will extend to infinity. All the points
Okay,
along
okay,
this
sir.
curve.
I think I mistakenly understand that that is isothermal line. Sorry,
This
sir.
is the isobar. So all the entries, whatever entries are lying inside this 50 kilopascal entry, all these entries lie on this horizontal line. And this isotherm,
Yes.
it corresponds to minus 46.3 degrees Celsius, 4.53 degrees Celsius. And successively we are scanning across different temperatures. But they all lie, all these points, so this all these points are intersections of different isotherms with 50 kilopascal line.
Yes, sir. I understood, sir. Thank you.
Okay. All right. So let's do another problem. Let's do another problem. So what problem should we do? Okay, let's do 3.41, 3.41. So it says the question is as follows. So we have a sealed container, and the sealed rigid vessel has a volume, total volume V is equal to 1 meter cube. And it contains, so this contains 2 kg water at 100 degrees Celsius. The vessel is now heated, so there is heating going on. So there is some heating going on. So the vessel is now heated. And the question says, if a safety pressure valve is to be installed, so this is a safety valve. So what maximum pressure should the safety valve be set at in order to have a max temperature of 200 degrees Celsius? This is the question. Okay. So in fact, let me get the digital version, and I claim, I don't know how to put this. I have no copyright claim, but I am sure when I put it on YouTube, it will be struck down. So let me stop sharing screen and let me magically paste the question from a certain source so that I don't get struck down. So this is what 3 point. Yeah, we need to do these things sometimes. In fact, I can just share this. No, what did I share? Yeah. So you're able to see the screen?
Yes. So still you are writing body. Yeah, yes, sir. Right, sir.
So this is the problem. Okay. So this is the problem. So a sealed rigid vessel has a volume of 1 meter cube and it contains 2 kilogram of water at 100 degrees Celsius as shown. So the vessel is now heated. If a safety pressure valve is to be installed, at what pressure should it be set in order to have a maximum temperature of 200 degrees Celsius? All right, so that's fine. I mean, let's draw the PV diagram. or let's draw the TV diagram, whichever is convenient, and let's see what exactly they're asking us to do. So let's do it on a PV diagram. So let's draw the initial condition. So what is the initial condition? So initial condition is T equal to 100 degrees Celsius. Okay, it's been given that water is at 100 degrees Celsius. What is the other property with which I can ascertain what the state
X
of
is
water
0.
is? No, not necessary.
The specific volume.
How do you figure out the specific volume?
No, sir, it can't be.
I mean, you were correct, but suddenly you changed your mind.
Sir,
Sir, 1 by 2. Specific.
1/2.
It will be 1 by 2. So V is equal to the total volume, which is 1 meter cube, divided by the total mass, which is 2 kg. This is 0.5 meter cube per kg. So on the PV diagram, okay, we must first know where the point is, that is T equal to 100 degrees Celsius and V equal to 0.5 meter cube per kg. So I mean, regardless of whatever you do, suppose the point is here. Suppose the point is here. If you recall, I told that this particular specific volume will be like 0.001 something, and this specific volume will be 0.8 or 0.9 something. So you can safely assume this is for water. This is only for water. So you can safely assume the point is over here. Actually, it doesn't matter whether the point is over here. So this is some isotherm. Let me draw it in this light blue. This is going to be some isotherm. Some isotherm. But in this case, we know that this is going to be 100 degrees Celsius isotherm. No problem. Because this point is 100 degrees Celsius and V equal to 0.5 meter cube per kg. Now, what happens when you actually seal everything? The process is sealed plus heated. When you seal something, obviously mass is not going to escape, so is the volume not going to change because it's a rigid vessel. So if the volume is fixed and the total mass of water inside is also fixed, so whatever the final state will be, it will obviously lie on a vertical line like this. Okay. So this particular line indicates heating of sealed vessel. This particular line, it represents the heating of a sealed vessel. And we bother with a maximum temperature of 200 degrees Celsius. We would like to know the pressure which corresponds to this. Fine, let me draw the 200 degrees Celsius isotherm over here. So this is T equal to 200 degrees Celsius isotherm. And wherever this particular line intersects the T equal to 200 line, the intersection of T equal to 200 isotherm and the green line, which is the isochoric process, this will represent V equal to 0.5 meter cube per kg. The intersection will represent a specific volume of 0.5 meter cube per kg and a temperature of 200 degrees Celsius. So the pressure corresponding to this particular state, the pressure which corresponds to pressure at 0.5 meter cube per kg and 200 degrees Celsius will be the pressure to which the valve must be set in order to have a maximum temperature of 200 degrees Celsius. Is this logic clear so far? Is whatever I've just
Yes, sir.
mentioned, does it make sense to everyone? Okay, so then our task is to find out specific volume 0.5 and temperature equal to this, and we must simply figure out the pressure. Fine, that's very easy. I mean, close this because see, we are just using it as a property evaluator, I can just not save anything, no problem. So let me just say P equal to pressure, steam, V equal to 0.5 and T equal to 200. All right, let's run.
Sir, your
Sir,
screen
the
is not there.
screen showing
Oh,
the TES one.
my bad. My bad, my bad. Let me let me share my entire screen now.
Yes, sir. Now it is.
Yes, sir. Now it's
So I just fetch the pressure of steam at V equal to 0.5 and T equal to 200. I just click on evaluate. It gives me a pressure of 426.8 kilopascal. So I have over here, so the pressure is 428 or 26.8.
hello, sir.
This, yes,
Sir, why you wrote steam there, not water?
it doesn't make a difference. Even if I put water, doesn't make a difference.
Okay, sir.
Okay, so this is how you can quickly do the problem using the computer. Yeah.
Sir, in this case, the x lies between 0 to 1. So if the x is like in the one region and I write water, then will it be a problem or?
No, 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 it will not create any problem.
So can you please also fetch this value using the table, because like I'm not sure if this point will lie inside the dome or not.
No, I will do it. I will do it using a table also. But I just would like to show the drastic difference in how quickly you can solve this problem if you have the computerized tables in front of you. But see, it doesn't matter where this point is, where this point, it doesn't matter. I've just drawn a schematic. Like I've mentioned this many times now. You must first understand how the process is going on a schematic. I mean, see, this you don't know in a schematic whether it started over here, ended over here, or for all you know, it started over here, ended over here. Who knows? But the point is, you must at least know what is going on. It's an isochoric process, and it should intersect the isotherm. Yes, it's an isochoric process, and it should intersect the isotherm. This much should be clear to everyone. Is it not?
Yes, sir.
So now we will do it using a manual table. All right, we will do it using a manual table. We'll do it live. This is the, you must always draw this. I mean, after a while, you may feel, you may make fun of this, that this guy, any problem is doing is making this ping shaped curve, but helps you visualize. So now the first thing that we would like to know is, I mean, we don't really want to know where the first point lies. So the first point, 100 degrees Celsius, I mean, most likely it lies inside the dome. Actually, this point corresponds to 0.5 meter cube per kg and 100 degrees Celsius. We don't care. I mean, whether this is inside, outside, who knows? All we care is this is the 200 degree Celsius isotherm, and whether this is the point, or I am drawing another possibility. This could be the 200 degrees Celsius isotherm. So whether this is a point. It could be either in the saturation dome or it could be in superheated region. So let's see. Let's go to the table. Let's go to the table. So we are looking for the property of V is equal to 0.5 meter cube per kg, and we are looking for T equal to 200 degrees Celsius. Let us assume first, let us assume that it lies inside the dome. Okay. So, or let us say we want to find out. Let me just erase this. Let me show you an easier way of figuring it out. Let me just erase this. Let us find out the temperature which corresponds to a specific volume of 0.5 meter cube per kg and x equal to 1. Let us first find out the temperature. So step 1, find it has become find T at 0.5 meter cube per kg and x equal to 1. All right, let's do that, no problem. So we go to water. Saturated water, temperature entries. We want temperature entries. But we don't. Okay, let's see. So we will look at saturated water pressure entry, and we will look at these specific volumes of vapor. The specific volume of vapor. Look, this value is very close. 0.49137, and the corresponding pressure is 375 kilopascal, and the corresponding temperature is. So let me zoom out. Let me take a snipping. So this is table B 1.2. It's very difficult to. The authors have. All right, is it visible? I mean, is the font too small? Let me know if it is too small.
Sir, if you are seeing on laptop, it's okay.
So let me see if I can. Okay, we can increase the size. Oh, it runs all over the place. That is the biggest problem. All right, all right, all right. So at a specific volume of 0.5 meter cube per kg and x equal to 1. So for x equal to 1, we are looking at all these entries. These are the entries of x equal to 1. Okay. And so we want at 0.5 meter cube per kg. So at 0.5 meter cube per kg x equal to 1, where do we have? These values are near 0.5. It is closer to, it is somewhere between 350 kilopascal, 375 kilopascal. So I will write down pressure 350. I mean, let's just take a ballpark of 360 kilopascal. The corresponding saturation temperature will be between 138.88 and 141 point. So let's take it as 140 degrees Celsius. Okay. So corresponding to this, the saturated vapor specific volume is something close to 0.5 meter cube per kg. All right. Very good. So what have we determined? That this particular point is at 140 degrees Celsius. This particular point is at, this is 140 degrees Celsius. You started off with 100 degrees Celsius. This is 140 degrees Celsius. And the corresponding pressure, this horizontal line, this corresponding pressure is 360 kilopascal. So what does it mean? In order to go to the 200 degrees Celsius isotherm, I must go further up. If I go further up along this vertical line, if I go further up, which domain will I be in? Will it be saturated dome or will it be a superheated vapor? What will it be?
Superheated vapor.
Superheated vapor.
This particular chain of thought should be clear to everyone. Everyone, like in this 60 odd people, this should be clear to everyone. Let me just get some random people in. I mean, I'm not calling you random, but you are randomly chosen, so it's random. Like Nikhil Jarpula. Navin Reddy, Jonalagadda. Madhugala Hemant Kumar. Poppula Monish. So all the Telugu people are absent or what? Basically. Vaishnav VS.
Yes, sir.
You are Vaishnav. So Vaishnav,
Okay, sir.
whatever I've discussed, does it make sense to you or not?
Yes, sir.
See, because all the other problems are just like remix of this. Okay, so I mean, so where are the others? I mean, Vaishnav does get it. That much I've understood. But where are the
Yes,
others?
sir.
Who is this? Madhugala Hemant Kumar.
Yes, sir.
Madhugala Hemant Kumar, why didn't you respond on time?
Sir, yeah, I think you have been telling all the names, sir. And after that, I
Okay. Angel Wilson is here. I think she was sick. But are you okay now? Saw your name on the medical bulletin. Well, I hope you're okay now. Abhinash, Anil Kumar, are you there?
Yes, sir.
Abhinash. So now you tell me what we should do. So we figured out that the final state is going to be in superheated vapor. So what should I do now? Step 2. What should be step 2? We are concerned, we want to find out the pressure which corresponds to the final state. So what should we do? Literally, like what should I do now? So what are the state points of this point?
So as it is in supercore, so we should find in table of superheated, sorry.
This is Aniruddha Bajaj's voice. I'm looking for Avinash Anil Kumar's voice. Avinash, tell us.
Yes, sir.
What should we do? What are the two state points which fully define this point over here? Guys, you should be able to answer this. Otherwise, there's no point in blaming me that I did not teach properly thermodynamics. If you're not paying attention, be ready to face the music. It's not a course where you memorize various definitions and just put them on paper. No, that's not how it's gonna be. Okay, so Anirudh Bajaj, please tell us.
So for that specific point, temperature is 200 and specific volume is 0.5.
Very good. So under these, for these two properties, I must then go to the superheated table and fetch the
Yes, sir.
pressure. All right. So I'm right now in saturated water. Let me go to superheated water. So now we are in superheated vapor. And in superheated vapor, I must first look at some pressure higher than 360 kilopascal. Okay. So these are pressures higher than, so this is 400 kilopascal. This is 500 kilopascal, right? This is 400 kilopascal. And I am concerned with the 200 degree Celsius line. So I will just, so it lies somewhere between 400 kilopascal and 500 kilopascal. So let me take a screenshot and explain why. Let me take a screenshot of this. See, right now you will see why doing these interpolations is not at all fun. Is this okay? First of all, so we are looking for V equal to 0.5 and T equal to 200 degrees Celsius. So now let us look at 200 degrees Celsius entries. All right, so let's look at 200 degrees Celsius entry. So for 500 kilopascal, at 200 degrees Celsius, the specific volume is 0.42492. Whereas for T equal to 200 degree, so there are no two T equal to 200 degrees Celsius entries over here. But we can expect that if we go from 500 kilopascal to 600 kilopascal, if you're looking at 200 degrees Celsius, so this line we extend 200 degrees Celsius, so the specific volume actually reduces. So what does that imply? What does this small observation imply? That obviously the pressure has to be lower than 500 kilopascal in order for us to get to a specific volume of 0.5 at T equal to 200 degrees Celsius. This should be your logical conclusion, right?
That
Yes, sir.
calculate
Yes, sir.
So let's see. At 400 kilopascal, we don't have any 200 degrees Celsius entry. So what do we do? How do we do it? So at 400 kilopascal, we have one point. First point, we have to interpolate. So at 400 kilopascal, the first point will be that at 143.63 degrees Celsius, we will have V equal to saturated vapor. The second point will be at 250 degrees Celsius, V will be equal to 0.59512. Now, how do I find out what this V equal to Vg will be? So I simply look up the 400 kilopascal saturated water entry and simply write down what V equal to Vg will be. That's actually pretty simple. So I will again go to the table. I will again go to saturated vapor temperature entries, and I will look at, okay, there's not 200 degrees Celsius entries. Oh, there is a 200 degrees Celsius. Okay, so 200 degrees Celsius. No, not
Can you
200.
please repeat this process? I got confused.
Yeah, wait. Let me just first write it down, then I'll explain what has happened. So at 400 kilopascal, we have a saturated vapor density of 0.46246, 0.46246 meter cube per kg. So it means that this point will be 0.46246. Okay. So now at 400 kilopascal, at 200 degrees Celsius, what is this specific volume? Who will do the interpolation? So it's like V minus 0.59512 divided by 200 minus 250 is equal to 0.46246 minus 0.59512 divided by 143.63 minus 250. So what is the value of V that you get from this? Point 46246 minus 0.59512 divided by 143.63 minus 250 bracket close multiplied by 200 minus 250 plus 0.59512. So it comes out to be 0.5.
0.5329.
So this specific volume comes out to be 0.5327 meter cube per kg. So what do we have? So at 400 kilopascal, 200 degrees Celsius, we have a specific volume of 0.5327 meter cube per kg. And at 500 kilopascal, at 200 degrees Celsius, we have a specific volume of 0.42492 meter cube per kg. And we want to know at what pressure, let's call it P at 200 degrees Celsius, what will be the pressure which corresponds to a value of 0.5 meter cube per kg. Alright, let's again do the interpolation. Let me do it in red this time. So it's P minus 500 divided by 0.5 minus 0.42492 is equal to 500 minus 400 divided by 0.5 minus 0.5327. So let me go to the calculator again. So it's 100 over 0.5 minus 0.5327 bracket close multiplied by 0.5 minus 0.42492. This plus 500 is equal to what? I'm getting a very wild answer. Did I
So
make
on
a...
the right hand side in the denominator, it would be 0.42492 minus
Oh,
0.5.
this is incorrect, right? So
Yes, sir.
do not make these mistakes. Do not make these mistakes. This would be 0.42492. All right. So 100 over 0.42492 minus 0.5327 multiplied by 0.5 minus 0.42492 is equal to this plus 500. So it comes out to be 430.34. This
Yes, sir.
pressure, it comes out to be 430.34 kilopascal. All right. So finally, we have that this pressure is 430 point something kilopascal. What had we obtained with the help of a computer? We obtained 426.
426.
So okay, there you go. So to the guy who was confused, let me tell you what happened. First of all, we established that we are not in the saturated dome. Who asked the question? Let's have a conversation with him.
Me, I'm Devik.
Your name is Derek.
Devik.
Devik, okay.
Yes, sir.
Okay, Derek. So Devik, look, this much was clear that we first ascertained that we are not in the saturated dome.
Yes, sir.
This much was clear. So it was clear that we now had to turn our attention to the superheated tables in order to ascertain what this point is.
Yes, sir.
But what was that point? That point was something which is at 200 degrees Celsius and something which has a specific volume of 0.5 meter cube per kg. This much also it was clear.
Yes, sir.
Now, what we did was we copied the steam table over here. We just took B 1.3 over here. And what did we observe? We just looked for entries of 0.5 meter cube per kg. So at 500 kilopascal, we had a first look at 500 kilopascal. At 200 degrees Celsius for 500 kilopascal, we observed that it corresponds to a specific volume of 0.42492. So for 500 kilopascal, 200 degrees Celsius, 500 kilopascal, T equal to 200, it corresponds to a specific volume of 0.42492. This much is clear? This entry.
So this we got after. Okay, no, sir. Yes, it's clear. It is clear.
Okay, then what did we see? Now, if we increase the pressure, if we go to 600 kilopascal at 200 degrees Celsius, it corresponds to a specific volume of 0.35202.
Yes, sir.
But we are looking for a specific volume of 0.5.
Okay, so it will be at some lower pressure.
So it will be at a lower pressure. Very good. So that was our conclusion. So we need to go to pressure of 400 kilopascal. But here is the catch. In the book, the entry for 200 degrees Celsius is not even given. The entries directly start from 250 degrees Celsius. We don't have an entry for 200 degrees Celsius. So first we must, so the first step that we did is we found out that for 400 kilopascal, 200 degrees Celsius, what this is going to be. And how did we find that out?
By interpolation. Like we could have taken any two values and then also do the same interpolation.
Well, it cannot be any two values. It cannot be, for example, between 250 and 300. That would be extrapolation. In order to do interpolation, we have to go between 250 degrees Celsius and the only point that is there as an entry in the book is 400 kilopascal and the saturation vapor point.
Okay, sir. Okay.
Basically,
Sir, excuse me, sir.
yeah,
Sir, the value at 200 is given in the previous page.
it is given in the previous page.
Yes, sir.
So that was a bunch of effort for nothing. 400 kilopascal. Oh, it is literally on the previous page. Oh, come on. Okay, so the value was there. It came out to be 0.53422.
So almost all temperatures after the saturation temperature will be most likely given in the table. Like
Yes. I was about to draw that. I was about to just draw that. Everyone, you can pay attention. I mean, this is not going to hurt you in any way. So, this is PV, and this is the isotherm. So, this particular point, after this particular point, all the entries along this vertical line are given. So, for 400 kilopascal, if we go into the table, 400 kilopascal, 143.63 is the isotherm. So this isotherm is 143.63 degrees Celsius. Then you will have 200 degrees Celsius isotherm. Then you will have 250 degrees Celsius isotherm and so on. So all the points on this curve, all the points on this curve, we should have a fair idea about. So I did not look at the previous table. So what did I do? I saw that there was a 250 degrees Celsius data point. We saw, and we had nothing. So I just, from the saturated water tables, I took this point. We took, and then we interpolated in between, and we found out the property at 200 degrees Celsius. Devik.
Yes, sir. I understood now.
But eventually, he did mention that there is a value at 200 degrees Celsius also, and it does come out to be very close to what we did through interpolation. Okay.
Yes, sir.
So then what did we have at 400 kilopascal? So what essentially later happened is at 400 kilopascal, 200 degrees Celsius, we found out a volume. Now these two are not at 0.5, so we need to interpolate between these two so that we can arrive at 0.5 meter cube per kg. So we did the interpolation and the pressure came out to be 430.34 kilopascal, which is very close to the solution that we also obtained with the help of a computer. Everyone in the class, just look at this lecture once again. If you are confused, don't be confused. Look at this again. If you have questions, we can discuss it tomorrow as well. No problem. But I will give you some practice problems. Make sure you do those practice problems. Only then will it be clear to you whether you have understood or not understood. This is the subject is like this. If you just look at me doing a bunch of problems, neither will I be benefited, neither will you be benefited, nor will you be benefited. So you must do it yourself. It's like watching someone like Sachin Tendulkar play a cover drive. You will feel like, okay, this is super easy. Just do it. When you go to do it, you'll end up all over the place. So you must do these problems. I will give you some practice problems. Please note them down. Please note the practice problems down. I will put it over here itself. So Sontag, 6th edition, do problem number 3.31, problem number 3.42, do problem number 3.44, problem number 3.62, problem 3.47, problem 3.63. I mean, ideally they are very small problems, and do problem 3.40 as well. Okay, do these problems. Do these problems. Everyone. Oh, I did not share my screen, did I?
Sir, but we noted down.
Okay, okay.
No, sir.
I'll share my screen. Okay, there you go. Practice problems. I'll share with you this file. I'll share with you the theory file as well. So I will ask you to do them on piece of paper so that the TA can also have a look if you're getting it or not getting it. I cannot take a risk, otherwise, in the end you will feel like I've not taught you well, but it boils down to you and you only. I cannot appear the exam on your behalf. So you must do the problem, you must understand the problem, you must be able to draw the schematics, PV diagram, TV diagram, whatever it is. Okay, you must do it. Only you can do it.
Sir, we can use EES, right?
You should do using both.
Okay.
ES are literally we wrapped up the problem in like less than a minute. Once the problem is conceptualized, it's just a matter of fetching the values. But the moment you want to do it through a table, you really need to understand which table to look at. And for that, we need to really have a very clear logic in our mind. Okay? Actually, to do the problem using ES also, you should have a very clear logic in your mind. But a computer helps you do things much faster. The easiest, if someone were to ask me what would be the fastest but qualitative way of doing a problem, who can tell what would be the fastest way of qualitatively solving the problem? Like not getting the exact decimal answers, but more or less you would understand.
Sir, the graph.
Yes, if someone were to give me everything as a graph paper, right? Each and everything as a graph paper, if I had. See, these tables and all is fine, but anyone can plot them as a graph. So if I had that, I could easily literally plot that this is the initial point, this is the process, This is the intersection with this particular line, so this is the final point. So that would have been the fastest. So you get it, what I mean. Okay?
Yes, sir.
It's a beautiful subject, and you don't treat it with fear or don't do that. Everyone should treat this subject as an art. I mean, I don't know. You should not be scared of it. You should be embracing it. Okay. Alright, guys. So I'll see you tomorrow at 9.
So thank you, sir.
Right. Have a good day. Please try
Thank
to
you,
solve
sir.
this problem. Huh?
Thank you, sir.
Thank you,
Bye.
sir.
Thank you.
Bye, sir.
Thank you, sir.
Alright. See you tomorrow.
Thank you, sir.
Thank you.